And I'm going to move forward now by going to section 2.3, where we're going to cover limits more analytically than we have so far. Okay, so when I say analytically, what we've done at this point is really a kind of quantitative or even qualitative approach to limits. And when I say those words, I mean we're not getting the exact answer. We're making good guesses based on somewhat unreliable information. The unreliable information that we're relying on are graphs, which graphs are limited to the fact that we can either hand draw them or even a computer can draw them only at a certain resolution. We can't zoom in infinitely at a point and know exactly what happens at that point. The other piece of information we used was tables. You're plugging in values into a formula as you get closer and closer to a number, but you can't do that and get infinitely close. You can only get as close as your calculator will allow or as much as you have time to do. Okay, so both of those can lead to wrong answers. So we want a better approach to doing limits, and there are some good ones. There's some nice limits that make life easy, but there are also some hard limits where we can't just plug in numbers. So the ones that we can plug in numbers, as you'll see in an example, come from the fact that we are able to take advantage of something called limit laws. Okay, and so I could go through and prove these. I'm not going to in this class. I will prove some of these if any of you end up taking a senior level undergraduate math class here called intermediate analysis, which is basically advanced calculus. It's calculus with all the proofs filled in all the way through sequences and series. We're not going to do all the proofs in here. So we're going to take advantage of the fact that occasionally I can say, just believe me. I hate doing that in a math class. You should not believe a professor just because he says it's true. But I'm going to claim that I will prove these for you if you stick around long enough in our program, or if you're a math major and you take those advanced classes. But for now, believe me when I say the following, 11 statements are absolutely mathematically rigorously true. Okay? These are called the limit laws, and they allow us to do some tricks with limits that make it easy. Okay? Even easier than you might expect. If you've done limits before, you'll recognize some of these, but it makes it fairly easy to work with limits. Okay? And so let me go through a few of these just so you can kind of see what it's saying. Number one, if you look at the structure of this formula, what this is saying is that if you have the limit of two things added together, two formulas, okay? So you have like two terms, and I'll give you an example. Look down here. You've got a 4x cubed and a plus 5, two things added together, okay? Then the limit of the sum, the limit of the whole thing, is the sum of each individual piece with the limit on it. You can basically, instead of taking the limit of the whole thing, you can take the limit of each piece. I can put the limit in front of each thing that's being added up. Okay, that's called the sum law, if you want to phrase it that way. But one of my favorite ways to express this is a little bit of verbal poetry. The limit of the sum so that's the limit as x goes to a of a sum of two functions is the sum of the limits. And that's slick. The limit of a sum is the sum of the limits. Say that with me. 1, 2, 3. The limit of the sum is the sum of the limits. Okay, so what would you say this one would be called? Number 2. If instead of a sum I have a minus, difference law. And how would you phrase that? I'm not going to write it out every time, but the limit of the difference is the difference of the limits. Okay. The next one we could call the constant law. Actually, I'm going to say it the constant multiple. There's another one that I might call the constant law below. This one's not quite as elegant to say, but notice the property here is that if you've got a constant times some function, you can pull that constant, whatever it is, whatever number is, outside of the limit. Okay, you can pull this C can come outside and it's written out front and it's the same thing. Okay, that is the value of the limit of a constant times a function is the constant times the limit of that function. So whenever you're taking limits, if you got constants inside, you can pull them outside. Okay, that's nice. You can't do that with all kinds of functions. Like you can't do that with square roots, right? Don't write this down, but you can't say the square root of 2x is 2 square roots of x, right? That's not the same thing. You can't pull constants out of everything, but you can with limits. In other words, the limit of 2x is 2 times the limit of x, no matter what x is going to. And that's nice, right? We like that about limits. Okay, the other thing we can do is products. So we'll call this the product law, and we'll call the next one the quotient law, where it's just like sums, right? The limit of a product is the product of the limits. You can put the limit on each piece. If 2 functions are multiplied together inside of a limit, you can take the limit of each one separately. The next one is the quotient rule, which works almost all the time if the limit of the function in the denominator is not 0, so you're not forced to divide by 0, then you can say that the limit of an f over a g, a quotient or a division of 2 functions, you can put the limit on top and the limit on bottom. Again, so long as the denominator doesn't go to 0. If you have a function raised to a power, you can also move the limit inside and take the limit of the function inside first and then raise it to a power. Okay, so that would be we'll call that the power law. I'm not going to name these two, but the limit of a constant, just think about what does a constant go to? If you're going to a specific value, not going out to infinity, but just like at a specific number, what does the height go to? Like if you have a function whose graph looks like this, it's straight across, it's always the same height, and here's your A, and the height is C, right? If you come in from either direction, notice you stay at that same height all the way through. So the limit of a constant is exactly that constant. Does that make sense? As opposed to going out to infinity in either direction, you're always staying at that same height. So the limit of, if there's no C inside here, then you can just get rid of the limit altogether. So the limit as x goes to, if I wrote down something like limit as x goes to 3 of 17. This 3 means really nothing. It doesn't do anything to the problem. The answer is 17, right? No matter what that constant is, as long as it doesn't depend on x. Okay, that's just kind of a side note. All right, if you have the limit as x goes to a of just the x by itself, that's going to be just a. That should make pretty good sense too, right? If you're looking at a function whose output is always its input, then as you get close to a, as your input gets close to a, your output gets close to a, right? Because x is just that function whose input and output are the same thing. You plug in 2, you get 2 out. You plug in 5, you get 5 out. So what happens as you get close to a with your input, your output gets close to a. So that makes sense, right? And then 9 is basically a combination of 6 and 8 together. Because if I take the limit as x goes to a of some x to the nth power, then it's basically the same as just plugging a into it. It's a to the nth power. Because if you ignore the n for a second, right, if you just cover that up, right, no a's are there, sorry, no n's are there, then it looks just like 8, right? But if I do x to the n, then I can just move the limit inside and first take the limit of x, which we know from 7 is going to be a, and then I'm going to take and raise it to the nth power after that. That's what I did right there. Easiest way to think of it is you can just plug it in, right? If you've got a formula in here, and I'm taking the limit as x goes to a, plug a into that formula for x. That works for powers. That works for roots, which is number 10. Call that the root law. And technically, both of these are examples of a root law. This one says if you're just got an x inside, you can just put the a in. This one says if you've got a formula for f inside the root, you can just take the limit of that formula underneath the root. Okay? So all I'm going to do then for the rest of this section is just a bunch of examples and show you how these limit laws make taking limits a lot easier than graphing or even tables. Okay? More often than not, in practice, when you come across a limit like this, it's not as easy as number 1 here, but let me walk you through the application of using the limit laws to answer this question, and then I'll show you how the limit laws basically give us a shortcut. Can you all see all right with the light on? I've turned off the overhead light before, but I think with the bright TV screen, it's about the same either way. Do I need to turn off the overhead light over this, or can y'all see okay? We're good? Now, eventually, there is going to be a screen over here that has the same thing, not hanging from the wall, but from a cart. But they ordered the cart, and we got 2 TVs. And as you saw, the first TV we got had that shadow on the bottom, so they sent off for the new TV. And the cart they got had a bent piece in it. So we're delayed on that. I'm not sure how long it will take IT to get those in. But it's coming, but hopefully everybody can see all right in here. You'll complain to me, please, if you have any issues, if I'm not writing big enough or I'm sloppy. Okay, so here's how I would formally and mathematically rigorously use the limit laws to find the value of this limit. The first thing I notice, like the final operation, kind of outer operation, is this sum, right? Kind of working my way backwards. If I see that there's a sum in here, then I can use number 1, it's called the sum law, and I can rewrite this as the limit as x goes to 2 of 4x cubed plus the limit as x goes to 2 of 5. Agreed? That is the limit of the sum is the sum of the limit. All right, so I've just split this now up into 2 limits. I'm going to look at the first one here, so I'll put this in blue right there. Which limit law can I apply to this one? Constant. The constant, which was number... The constant says I can take the 4 and pull it outside, right? So this is 4 limit as x goes to 2 of x cubed. And say, what about this one right here? Which limit law can I apply there? 7, which says that is, it's just 5, right? Because it's the limit of a constant, right? So right now I've completely simplified this limit into just 5, and I've simplified the first part of that into 4 limit of x cubed. Now what limit law can I apply to this guy right here? 9, I can use 6 and 8 together, or 9 is the one that tells me I can just write that as whatever the value that it's going to the nth power. In this case, the 4 stays there, but then I can take the 2 and stick it in, right? That limit as x goes to 2 of x to the 3rd is 2 to the 3rd, and that's using, what did I say, 9? which at this point I can just do arithmetic, right? 4 times 2 cubed, which is 8 plus 5. That's 32 plus 5, which is a value of 37. So this is simply an application of each of the limit laws that apply as you go. And hopefully you see this. You can actually think of all of that together in one big step, that if you go from here to here, you basically plugged in x equals 2. Right? You plugged in what the limit was into that formula. That's what this process allowed you to do. And in general, so long as you get a nice number out of it, what we've just learned is that the limit laws tell us every algebraic expression inside of a limit can be found by just plugging the thing that x is going to into that formula, right? So long as that gives you a number out. All the algebraic operations, addition, subtraction, multiplication, division, exponentiation, and roots, you can just plug the limit value into the actual function in the limit, and the answer is the value of that limit. That's what this formula on the right-hand side gets close to as x gets close to 2. Easy peasy. That's nice. That's what the limit laws allow us to do. Okay? So let's try number 2. Same process. Instead of going through each of the limit laws, let me just do what I did with the black arrow. Let's skip straight to the end. Okay, what would you do? You take, what value would you plug in for x? Negative 3. So negative 3 squared minus 9 over negative 3 plus 5. Algebra gives me what? 0 over 2, right? But 0 over 2 is just, there you go. 0 divided by anything, as long as it's not 0, is 0. Just that easy. But is it always just that easy? Of course not. Life is never always just that easy. In fact, it would be boring. We wouldn't teach a whole class if everything was easy. Anything worthwhile is challenging. So let's turn the dial up a little bit, kick it up a notch. What happens here? You do the same thing. You end up with negative 3 squared minus 9 over negative 3 squared plus a minus 3 minus 6. And on top, I get 9 minus 9, right? 9 minus 9. And on bottom, I get 9 minus 3 minus 6, which is over 0. Okay? So we have an issue here, and I'm going to put a little thought bubble off to the side here. 0 over 0 case essentially means we need to do more algebra. So this is not an answer, okay? This means we're not done. Because 0 divided by 0 is not 0. 0 over 0 is an indeterminate thing, okay? Because we can't divide by 0, so that doesn't make any sense. It turns out that if you get 0 over 0, that means the answer can actually end up being anything. The answer can be any number. The answer could end up being does not exist. The answer could be positive infinity. The answer could be negative infinity. 0 over 0 means we have no clue what the answer is and we have more work to do. It doesn't mean that it doesn't exist. There's actually an answer on this problem, okay? But there's some of them, when you get 0 over 0, the answer is does not exist. There's some of them where the answer is positive infinity, negative infinity. The point is, when you see 0 over 0, realize you basically got to start over. Okay, that's not going to work. So we got to do something different. So I'm going to show you some tricks for the rest of this section, what we'll work on in practice at 11, what tricks can we apply, what kind of algebra can we do to find the answer in a situation like this. And I don't want to go back to graphs and tables. I still want to do it analytically. So what I'm basically going to do is do some algebraic simplification on these. Okay? In this particular case, what do you think you might be able to do to make this simplify? Factor. Right? I recognize right away, as I'm sure many of you, difference of squares on top and a trinomial on bottom, and if we're lucky, they have a common factor which we can cancel out. Some of you probably already see it, right? Let's write it down again. So limit as x goes to -3, and now let's factor the top and factor the bottom. What is x squared minus 9 factored? Difference of squares. So x plus 3, x minus 3. Very good. Very good. And on bottom, if you have some trouble factoring, feel free to come ask, but I'm going to assume you guys can do factoring by this point in your mathematical career. I'm going to do a kind of reverse FOIL or trial and error method here. I know the first two have to multiply together to give me x. This sign right here tells me they're opposite signs. I can do 1, 6, 2, or 3. And they got to add together for the outside and the inside to give me a +1. So 3 is positive and 2 is negative. If you have box methods or other, grouping methods, whatever you're comfortable with for factoring, but you got to be able to factor. What do you notice? Those cancel out. So let me make a note. This is separate from the problem here. I just want to make a comment about this problem. I think I have a question like this in the homework. If I have x squared minus 9 over x squared plus x minus 6, and I have x minus 9, nope. This was supposed to be a 3, right? That's a 3? No. So if I have x minus 3 over x minus 2. Okay, I'm about to write that this is equal to the limit as x goes to -3 of x minus 3 over x minus 2. Okay, this statement up here is a true statement, but this right here is not. That is, this over here is not equal to this. They're not the same function. Okay, I can say that their limits are the same, but what I cannot say is they're the actual same function. Even though I canceled, it looks like, well, I just canceled those things out. The problem here is that these two formulas are different at x equals -3, right? The one on the left-hand side, if I plug in -3, what do I get? 0 over 0. If I plug in -3 over here, I'm going to get an answer, right? So they can't possibly be the same thing if I get two different answers for the same x, right? So they're not the exact same. They're same everywhere except -3. So it's just important because you're at a more advanced mathematical level now for you to know as a calculus student that even though I can cancel the x plus 3's and the limits of those two functions are the same, the actual functions themselves aren't identically the same function. Okay? But that's just a comment. It doesn't change your answer on a calculus problem with limits because now you can just plug in the -3 and you'll get the right answer. -3 plugged into here gives me -3 minus 3 over -3 minus 2, which is -6 over -5. Of course, the negatives can then cancel, and you've got 6/5. So strategy number 1 here, just things to try, is to try factor and cancel. And when I say strategy, I mean how do we respond to the 0 over 0 case, right? 0 over 0 case, strategy 1, factor and cancel. Everybody okay with 6/5? Okay, so next problem. First try, you could throw in an h equals 0. I've mistyped this, by the way. Do me a favor. Move my square from inside the parentheses to outside the parentheses. That was a typo. It's not the problem I wanted to do. The first problem is not interesting. This problem is interesting. So if I put the square on the outside, now what happens as h goes to 0? If you plug in h equals 0, what do you get? 0 over 0. Because 4 plus 0 is 4. So 4 squared is 16. 16 minus 16 is 0. And the bottom is 0. Okay? So this is the 0 over 0 case. So what would you do then to try to algebraically simplify that? Suggestions? Any ideas? I know I can't just plug in, so I've got 4 plus h squared minus 16 over h. What am I going to do to that?
Quotient law?
Say that again?
Use the quotient law?
So take the limit of the top over the limit of the bottom? Yes, I could. If I rewrite this as limit of 4 plus h squared minus 16 as h goes to 0 over the limit as h goes to 0 of h. That was the suggestion I heard. It's still 0 over 0, isn't it? Because even if you ignore the bottom and do the top by itself, you get 0, and then you do the bottom by itself, you get 0. So really, I was kind of already using the quotient rule in my head. We've just written it out now. So we still end up getting to 0 over 0, which is a dead end. So let's try something else.
Say we could do it out, like you did an algebra problem. Could we solve for 0, like put 0 on the right side and then?
Putting 0 on the right side implies that we know the answer is going to be 0, right? Which we don't. It's a good thought, though. If we knew what the answer was, we could figure it out that way. But that's not, we don't know what the actual answer is equal to. We know it's the input that has to be 0. The h has to get close to 0. So,
You could do the opposite of that.
so multiply it out,
Yeah.
expand.
Yeah.
So let's take this guy and expand him. Okay. So you remember how to take 4 plus h and square it?
Yeah.
What is that?
H squared plus 8h plus 16.
So you can think of it as a FOIL problem, 4 plus h, 4 plus h. Actually, h plus 4 gives me the order you've got here, but we're just going to rearrange the terms anyway, so it works out to be the same. 4 times 4 is the 16. 4h plus 4h is the 8h, and the h times h is the h squared. So keep the limit out front, because we haven't taken the limit yet. But on top, Boston has come up with h squared plus 8h plus 16. That's this first piece, right? And then there's still this minus 16 there and an h. Okay? Did that help? It's still 0 over 0, isn't it? Anything else I can do from there? Maybe if I don't think we've reached a dead end yet, because I think there's still something I might could do to this guy. Well, you can't cancel an h on bottom unless the h is in every term on top. You see the 16s? 16 minus 16, those are like terms, so you can subtract them out. And then, Thad, what you said does work, because you do have h's all the way across. In fact, I could factor the top by pulling out that common factor. right? Limit, this is equal to limit as h goes to 0. Pull out, they both have an h in common. If you pull that out, what are you left with?
H plus 8.
And on bottom, you've got just an h. And now, h times the whole numerator and h on bottom means that I can cancel. You just got to be careful when you say, can I cancel those? Before, I can't cancel an h when there's terms up here that don't have h's in them. But I can if it's times the whole thing. And so now what I've got is the limit as h goes to 0 of h plus 8, which is, that does work. So maybe strategy 2, to use Boston's language, is to reverse factor, or as we sometimes call it in algebra, expand. Side note, or just a comment here, you can't always see the end from the beginning, okay? There's very few times when I'm working a challenging calculus problem that I know how it's going to end, or that I know what path I'm going to take to get there. It's important that you learn in calculus that we are a try it and see kind of mentality. Let's use the rules that we know. Let's use the skills that we've developed and see what happens and see if we get closer. More often than not, we may get further away and we have to start over, but we'll try something else the next time, okay? It's like going to battle against a dragon and you don't know which weapon is going to take down that particular foe. We're going to try what we can. If it doesn't work, we go back and start over and try something new. That was a great strategy we got there. All right, let's talk about piecewise functions. Now, I'm not actually asking you to graph this. I just want you to think in terms of limits of what's happening. Part A says, for this particular f of x, find the limit as x goes to 1 of f of x. What do you think we should do there? What does this function get close to as x gets close to 1? And how did you get there?
I put 1 in for the top one.
Okay, so noticing 1 here satisfies that condition, right? So this formula at at x equals 1, f of 1, would just use this top piece, right? So I'm going to do the same thing I would have done at the very beginning. Just plug in 1 and see if it gives me a number, right? And f of 1 in this case is the top formula with 1 plugged in, right? Because it says if x is less than or equal to 2, which 1 is less than or equal to 2, then use this formula. And if x is greater than 2, use this formula. So f of 1 would be 1 cubed minus 2 times 1 plus 4, which is 1 minus 2 plus 4. 1 minus 2 is -1, right? And then plus 4 is, we get 3? But and you had the right approach. We just did some arithmetic, I think, was the only mistake there.
I did it in my head.
It happens. But that, everybody agree with that? Make sense to you? Just do f of 1 if you can. Now, if I get a 0 over 0, or I'm at a place where the function is at a breakpoint, I got to do something different. By breakpoint, I mean these guys right here at 2. If I want to find the limit as x goes to 2 of f of x, I can't just find f of 2 because it's going to be different as I come in from the left-hand side to 2 than if I come in from the right-hand side to 2, right? So in this case, I've got to break this up into 2 different pieces. I got to do the limit as x goes to 2 from the left, and I've got to do the limit as x goes to 2 from the right. And again, why do I have to do it from both directions on this one when I didn't on A? Well, on A, it was not a breakpoint. From the left and from the right, it's the same formula, right? But at 2, if I come in from the left, from less than 2, I'm going to use the top formula. But if I come in from the right, if I come in values that are bigger than 2, I'm going to be using the bottom formula.
Even though the bottom formula never equals 2.
Never equals 2. Remember that with limits, what happens at 2 doesn't matter. That's the thing about limits, is what happens at that point, it doesn't even matter. That was the reason, by the way, back up here on number 3, that I didn't care that the value at -3 was 0 over 0. It's only what happens when you come in from both sides. So what happens at the point doesn't matter. It's what happens when you get close. So that's how we can get away with the fact that we really don't care what happens at 2, just when you get close to 2. So we're going to come in from the left, that is from the minus sign, from less than 2. And if your x is less than 2, you use the formula up here, right? So this one becomes 2 cubed minus 2 times 2 plus 4. Notice I'm just plugging 2 into the top piece, because that's where x is less than 2. And if I come in from the right, what does that look like?
3 times 2 minus 2.
And so this value gives me 8 minus 4 plus 4, or just 8. And this one over here gives me 6 minus 2, which is 4. Maybe I shouldn't put a box around the answer, because that's just part of my answer. So the limit from the left is 8. The limit from the right is 4. What does that say about the limit at that point? Because those are not equal. If they were the same, then that would be your answer. But if they're different, that means you've got a break at that point. So if I come in from one direction and from a different direction, I got a different height, then the limit doesn't exist. Does that make sense? So you have to do the limit from each side if you're going to have a piecewise, or when you have a piecewise defined function and the x is approaching one of the breakpoints. If it's somewhere in the middle and not at one of the breakpoints, then you don't have to worry about it. That's just like finding the limit of just that function, that one piece by itself. Questions? Okay. This one doesn't look like a piecewise function, but it actually ends up having to be done the same way. The limit as x goes to 3 of the absolute value of x minus 3 over x minus 3. Think about the limit as x goes to 3 from the left. And the limit as x goes to 3 from the right. So when you're coming in from the left, right, whenever x is less than 3, what happens when you plug in something less than 3 into this absolute value? It becomes positive, right? But it's negative inside, but then it becomes positive. You switch the sign of it, right? So in fact, this is the same as you take x minus 3 and make it negative on top. Agreed? I mean, think about that. If what you're saying is whenever x is less than 3, the thing inside is negative, and then you want to make it positive, so you just switch the sign. These two right here are the same thing then. That's a neat little trick that I can do with absolute values. What happens then over on this side if x is a little bit bigger than 3? It stays positive. It stays the same. This is the same when you're coming in from the right and the x is a little bit bigger than 3, x minus 3 over x minus 3. This one's negative because inside is negative, and you got to make it positive to be an absolute value. The answer to an absolute value is always the positive version of the thing inside. And since if I'm less than 3, then this is going to be negative, so I put a minus outside to make it positive. But then you can look at the algebra here. What does this turn into? What is negative x minus 3 over x minus 3? I can cancel. It's just negative 1. It's the limit as x goes to 3 from the minus of negative 1. And what happens to this one? It's just positive 1, right? And so this one is negative 1, and this one is positive 1. And so what does that say the answer to that limit is? Does not exist. Okay, so let's see. We did, I should write this down at the top. I'm going to do strategy up here. This was strategy, what is this, number 3? Okay. On piecewise at the breakpoints, do the limit from each side. So when you're piecewise at the breakpoints, that's the kind of problem that you've got. Do the limit from each side. That's my suggestion on piecewise functions. So again, strategy number 3, piecewise at the breakpoints, do the limit from each side. On absolute values, so maybe strategy number 4, rewrite absolute values without the absolute value. So basically you're thinking of absolute value of x is negative x when x is less than 0 and positive x when x is greater than 0. So that's the strategy that I used there. I hope that helps. That really it boils down to the fact that you're thinking about what the value of the absolute value is inside when you're slightly less than the number, right? So x is less than 3, you have a negative, so you can rewrite it as a negative x minus 3. Positive, you can write it as just x minus 3, and then we do the algebra from there. All right. Let me keep going. I know because we got the 11 o'clock hour, I'm going to keep going and then we'll take a break after I get done with the notes, okay? So I've still got a couple of examples, and then we got to talk about the squeeze theorem. So let's finish this and then break, and then we'll come back and do some practice problems together. All right. Everybody caught up? Do I need to go back to any notes? Or are we ready to go on to the next problem? Yes? Good, 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 good. Okay. So we're going to try to find the limit as x goes to 2 of this guy. First of all, do you remember what raising something to the negative 1 power means? It's the inverse. It's the reciprocal as a fraction. If it was a fraction, it means to flip it. You can think of this as 1 over x. X to the minus 1 just means 1 over x. Negative exponents mean move it to the bottom of a fraction. Like just, you'll remember from algebra, if I said like find 2 to the negative 3, that means 1 over 2 to the 3rd. So x to the minus 1 means 1 over x to the 1st. And that gives us then a clue that we have a problem, because if I plug in 2 into this, right, 2 to the minus 1 minus 0.5 over 2 minus 2, It's a 0 over 0 case. So we need to do something algebraic to simplify this. I'm going to rewrite this as 1 over x minus a half divided by x minus 2. Because 0.5 is just half, right? All right. At some point in your algebra classes, whether algebra 2 in high school, or if you took college algebra with us or another university, you had these complex fractions, fractions inside fractions. I would use the algebra I learned from that point in my classes to simplify this. Do you remember how you simplify? There's multiple ways to do it, but how do you simplify a fraction inside a fraction? Okay, so we could combine these on top into one fraction. And then if you have one fraction divided by another fraction, you can do the invert and multiply trick, right? So that works. One of the strategies I taught in my algebra class was to find the lowest common denominator of all the kind of inside fractions and just multiply through by that to get rid of all of them. Two different strategies that do the same thing. I'm going to do what Thad suggested, which he said was to find a common denominator to combine those fractions. So what is the common denominator of 1 over x and 1/2?
2x.
And so what's missing from the first one? So multiply by 2 over 2. Multiply this one by x over x. And on top you end up with 2 minus x over 2x divided by x minus 2. And there's still a limit as x goes to 2. Again, my strategy was to think of this as a fraction on bottom, so now I'm just dividing two fractions, right? And do you remember how you divide fractions? Copy, dot, flip. Take the bottom one, flip it, and multiply times the top one. So this becomes the limit as x goes to 2 of 2 minus x over 2x times 1 over x minus 2. What can I do there? This cancels with this, kinda. They both have x's, they both have 2's, but they're reverse of each other, right? In fact, all the signs are opposite. This is a minus x, that's a positive x. This is a plus 2 or positive 2, that's a minus 2. So you can cancel those out, but it leaves behind something. It leaves behind the negative. Because you can, one way to think of it is like if I rewrote this one right here, I'll do this in a different color just so you can see it. This right here is negative x plus 2, right? And if I pull out a negative from it, it's a positive x and a minus 2. Right? You see that? So this right here is actually minus x minus 2, which means it cancels with this but leaves behind that minus. So what I've got is the limit as x goes to 2 of negative 1 over 2x. And every point up to this point, if I'd plugged in 2, I'd gotten 0 over 0, but now I can go ahead and plug in 2. Right? Plugging in 2 gives me negative 1/4. Booyah. So for complex fractions, I would say combine fractions with the LCD. There's another good strategy to have. Did my factoring make sense? That's one we cover in algebra, but it's one that you don't see that often, so it's easy to forget. It's just a little trick that says if every term has the opposite sign, then you can cancel them out, and it leaves behind a minus sign. Fabulous. Good? Yes? All right. One more strategy problem, and then I got to talk the squeeze theorem. So really, two more strategies. I love the squeeze theorem. Makes me think of orange juice. All right, what about this guy? Again, plugging in 0. It's a 0 over 0 case, right? Which means we need to do some algebra. I have the square root of 3 minus x minus the square root of 3 all over x. Does anybody have any suggestions as to what we might do to simplify this guy? Or at least, maybe not simplify him, but modify him, change him. Kind of. You're on the right track in that we want to get rid of the roots. That's the right goal. The problem with squaring it is squaring things changes their value, right? If you have an equation like, something equals something else, we're allowed to square both sides, because if two things are equal, then the square of the thing on the right is equal to the square of the thing on the left, right? Now what you can't do is a fraction like that. If I start with a fraction 2/3 and I square the top and bottom and I get 4/9, those are now two different fractions, right? So you can't take a fraction and just square it on top and square it on bottom and say it's still equal, because it's not, right? Does that make sense? So that I can't square top and bottom. I can square both sides of equations, but I can't square top and bottom of fractions and still claim it's equal. You can multiply the top and bottom of a fraction by the same thing, right? If I multiply the top by 2 and the bottom by 2, it stays the same fraction, right? But I can't just square the top and bottom. So yes, with the goal, but not the way that you said to get there. What else could we might do to try to get rid of some radicals?
You turn it into an exponent?
So you're thinking like 3 minus x to the 1/2 minus 3 to the 1/2. Okay, that is true. But then what?
Yeah.
Okay, that is true. So that's one of those things where let's try it, but then I don't know what to do next. I also don't know what to do next. So from this point, I'll let the whole class look at either this one or this one, and do you have any suggestions about what we might could do? Multiply by the same thing on top and bottom, and you want to choose this?
Yeah.
Okay, so we could multiply by, if you've got a pencil, write this in pencil. If you're writing in pen, don't write down what I'm about to write down. I didn't mean to give away the fact that it's wrong. I will say it is very close to what we will eventually want to do, or what I would suggest that we do. I'm not saying there's only one way to do this. So this is now equal to the original problem because I multiplied by the same thing on top and bottom. All right. What is kind of interesting about this is that I can still FOIL, like first, outside, inside, and last, the top. The firsts have the effect of getting rid of the radical. right? Because the square root of 3 minus x times the square root of 3 minus x is 3 minus x with no radical, right? And the last square root of 3 times square root of 3 is just 3, because that's square root of 9, right, which is 3. But the outside and the inside, I get a minus square root of 3 times square root of 3 minus x, and a minus square root of 3 times a minus square root of 3 minus x. So I get two of those things, okay? And they're the same sign, so they add up, right? What would happen if I did this? It gets rid of the middle term, right? On top, at least, right? Because if I multiply the outside, I got a plus square root of 3 times square root of 3 minus x, and on the insides, I got a minus square root of 3 square root of 3 minus x. Those end up canceling each other out, right? It's like a difference of squares. So now, those of you with your pen can write down exactly what I have here on the screen, because this will work. So my strategy here is that when you see a difference of radicals, you can get rid of those radicals, or at least you can cancel them out by multiplying by the same two terms, but change the middle sign. There's a word for that you learn in complex variables, but also in this context when you're rationalizing radicals. That word for switching the middle sign is called the conjugate. So strategy number 6 here, multiply by the conjugate. Have you heard the word conjugate before? Sound familiar? No, not at all. Well, if you have a plus b, a minus b is the conjugate. Okay, so if I have square root of 3 minus square root of 3, sorry, square root of 3 minus x minus square root of 3, then its conjugate is square root of 3 minus x plus the square root of 3. Okay, so two terms that have radicals in it, I change the sign between them, and now the difference of squares is basically canceling the middle term out. Okay, I'm going to erase Alex's suggestion here because I think we're making progress. What do we have? We have the limit as x goes to 0 of the firsts. Give me just 3 minus x, because the square root of 3 minus x times the square root of 3 minus x is the square root of 3 minus x squared, which is just 3 minus x. And then the outside and the inside cancel, and then I have a minus 3. Right? Square root of 3 times square root of 3 is square root of 9, which is just 3. Does that make sense? And then still got a bottom. So I really haven't gotten rid of the radicals. I only got rid of them on top. But something cool is going to happen here in this particular example. And I'm not going to multiply it out. I'm just going to leave it written out factored because it actually helps me to leave it like this. This limit is equal to this limit. So again, what I did was I chose the end of the fraction that had two terms with a minus, and I changed the sign to a plus and multiplied by the same thing on top and bottom. And then what happens on top if you do the algebra, combining like terms? So this is just, you can get rid of the parentheses because there's just a 1 in front. 3 minus x minus 3. So the 3's cancel, and you're left with minus x. And on bottom you have x times square root of 3 minus x plus square root of 3. Yep, if I tried to plug in 0, I still get 0 over 0, but now if I cancel out those x's, I now have a problem that I can just plug the number into. Square root of 3 minus x plus square root of 3. Dun, da, da, da. What do we get now when we plug in 0? I'll go ahead and write it out first. because this is square root of 3 minus 0, right? That's square root of 3 plus square root of 3. Just plug in 0. Like that. Which is negative 1 over square root of 3 plus square root of 3, which is negative 1 over 2 square roots of 3. I saved that one for last because it's one of the more tricky ones, but you see the strategy that we applied here in practice. You'll get to practice with one of those here in a little bit on your own. Did I lose you? That one's tricky. It's just, it's algebra, right? But it's still algebra in the context of now limits. The reason we're using this technique is so that we can now plug in the value of x after it's been simplified. All right, I'm going to give you one more weapon to battle your dragons with. And this last example I'm going to give you is called the Squeeze Theorem. It doesn't seem in the way that I've written it here that it's going to be all that useful, but in fact it turns out in many cases to be the only thing that works. I want you to peek ahead and look at this problem here that we're going to actually plug into. This limit as x goes to 0 of x squared sine of 1 over x. The problem with plugging 0 into this is you get a 0 times a sine of 1 over 0, which is like the sine of something going to infinity. This sine is like bouncing back and forth. And so the sine makes this one messy, and we don't really know what's happening. And so what we want to do is take advantage of maybe some knowledge we have about the functions that are involved. Here's what the Squeeze Theorem says. Look at this picture that I have right here, and imagine that you know the answer to the limit for h and for f. So the Squeeze Theorem works when you know something about what's above the function and what's below the function. Let's say we can't figure out g, but we know how to figure out the limit for h and the limit for f. Okay, and what we're specifically looking at is what happens as x goes to a from both sides. Okay, and again, I'm going to claim I know what happens to f, and I'm going to claim that I know what happens for h. And this is the other thing that I know, that g is always between those two functions, always, okay? Or at least for some interval around a, g is in between h. That is, vertically, g is in between h. We don't care really that over here it crosses over because we're looking about what happens close to a. So near a, g is always between f and h. And so over here, all right, those three values, we've got that the g of this particular x is somewhere between the h of x and the f of x. But as x gets close to a, both the height of g and the height of h are getting closer and closer to this L. And as I come in from the right-hand side, the same thing is happening. That is, as I move towards the middle here, as I move along this line, this is also going to a height of L. So the limit as x goes to a of f of x is L, and the limit as x goes to a of h of x is also L. If g is always between those two, then the Squeeze Theorem says we know that the limit as x goes to a of g of x also has to be L. Because it's between them, it's squeezed between, it's a sandwich, it squeezes it in. Okay? So we know, even if we didn't know anything about g, we now know because g is between h and f, that it's always going to end up between those two. So how do I use the Squeeze Theorem in practice? The answer is I use things that I know about functions like sine. You remember sine from your trig functions, right? What does the graph of sine look like? Everybody's doing this, right? It's the wave. Okay. What's the highest point? And what's the lowest point? And no matter what value of x you plug in, right, sine of anything is always between what two values? -1 and +1. Agreed? Even if there's a 1 over x inside here or any formula whatsoever, the output of sine is always between those two values. So here's how we use the squeeze function or the squeeze theorem. I'm going to write down x squared sine of 1 over x. And I'm going to tell you that I know about my sine that the biggest this piece will ever be is -1, right? Sorry, biggest it will ever be is +1. So this whole formula, if I replace the sine of 1 over x with +1, I get x squared times 1, right? That's the biggest this whole formula will ever be is this, because sine is never bigger than 1. And what's the smallest it will ever be? X squared times a -1. In other words, x squared sine of 1 over x is between -x squared and +x squared. Now I'm trying to find the limit as x goes to 0 of this middle guy. So let's take the limit of all three of these. The limit as x goes to 0 of -x squared has to be less than the limit as x goes to 0 of x squared sine of 1 over x. Again, I'm just taking the limit as x goes to 0 of each of these three pieces now. What I don't know is what happens to the middle, but I can figure these out because of the limit laws. What's the left-hand side? And what's the right-hand side? So if they both go to 0, what does that mean this has to be? That's the squeeze theorem. If you can figure out a triple inequality like this, where the left-hand side and the right-hand side go to the same value, then the middle one has to go to that value by the squeeze theorem.